Hey students, welcome to math this morning. It's Mrs. Baker. We're going to go ahead and go over your systems of equations foldable together. So if you don't already, make sure that you have a foldable and you'll need a pair of scissors, at least one pair per table. So pause the video now if you need to get either of those items. And then we're going to go ahead and review what we know about systems already. So remember that when we're working with systems of equations, we're working with two equations at the same time. So we're trying to find out if and when those two equations will ever meet. And when they do meet, that means that they both share that same coordinate as a solution. So if two lines touched at the coordinate 2, 3, 2 and 3 would be a solution for the x and y values of both of those equations. All right, so today we're looking at these systems, the three different types of solutions you can have for a system. So you can have one solution where the line touches one time. You can have no solutions where the lines will never, ever, ever touch. Or you can have infinite solutions where the lines are going to touch infinitely. And these three sections of your foldable are the parts we're going to fill in. And then we're going to graph the lines on these three graphs as examples. So first, go ahead and pause this video to make a cut line so you can have three different flaps along these bars right here. So you'll just need two flaps, and you don't need to cut down here. So these are going to be the pieces that fold open, and then the label should be on the back of that. So if you need to, pause the video to make those cuts. Otherwise, we're going to keep going with filling in the blanks. All right, so let's go ahead and take a look. We have our first example right here, and they've given us two equations. Remember, systems, we're always working with more than one equation. And we are going to fill in these blanks. So the slopes are blank. Take a look at the slopes here. We have the number before the variable, and these represent the slope. So this one's -2, this one's +2. What would you say about those slopes? Hopefully you would say that they're different. So we're going to go ahead and type different. Actually, I'm going to type, you're going to write. The slopes are different. And the y-intercepts may or may not be the same. This is super important. This part right here is super important. So if you can, highlight that, star that. This is what's going to, this portion right here is what's going to tell you that every time you see this scenario, there's going to be one solution for your systems. When graphed, the two lines right here intersect. And that means because they intersect, there is one point, x and y, which is just a coordinate, where they intersect, so there is only one solution. Okay, so when you graph these lines, there's only going to be one place where they intersect. And we're going to graph them now. So if you need to, pause the video to fill in these blanks, make sure they're filled in completely. And then we're going to graph them and find our solution. Okay, hopefully you're ready to graph. I'm going to do this first equation in red. And if you have a different colored pen or pencil you want to follow along with in a different color, you're more than welcome to do so. So I'm going to do this first equation in red. And we always start at the y-intercept whenever we are graphing. So I'm going to start at -3. So I'm going to go down 1, 2, 3. And then I know that my slope needs to be going down 2 over 1. So this is going to be my line right here. And I'm going to extend it, pretending I can see it. Keep going here. It'll be something like this. Remember, you are supposed to have the arrows at both ends of your line, so I'm going to draw those on here. Ooh, sorry, that's not very good. Okay, hopefully that's better. Arrows on both ends of your line because the line goes on for infinity in both directions. Okay, so this one's done and that one's in red. We're going to do the next one in blue. So the second equation is going to be in blue. And y equals 2x plus 1. Again, we start at the y-intercept, which is this positive 1. So we're going to start at 1. And our slope this time is positive 2. So that means we're going to rise 2, run 1. So I can do it again. Rise 2, run 1. Right here. And just like I did a rise 2, run 1, I could technically run backwards 1, fall down 2, and go backwards 1 and fall down 2. It's the same thing. And hopefully you see already that they intersect, and that's great. That's what we're looking for. So because red and blue make purple, I'm going to go ahead and put this one in purple. So this point right here where they intersect, they both touch right there. And that is the coordinate -1, -1. So the solution for this one is -1, -1. So this is what happens when there's one solution. Okay, we're going to move on to the next one and figure out what's happening in this system. With this one, I'm actually going to start with the graphing. So we're going to keep the red and blue lines. Hopefully that's helpful for you. So we're going to start here with the first equation. And remember, whenever we're starting with an equation that's already in slope-intercept form, it's given us the intercept and it's given us the slope. So we have to go down 3, starting on -3, and we're going to rise 2, run 1. Rise 2, run 1. And then keep going. It's important to extend your lines as far as you can when you're graphing systems because you don't know where they're going to intersect, so you want to kind of cover all of your bases. Okay, and then don't forget to add your arrows. So it's not just a line segment. And then we're going to do our blue line, y equals 2x plus 1. And let's see, so we're starting on the y-intercept, which is +1. And we're going to rise 2, run 2. Rise 2, run 2. It's about like this. All right, we're going to add the arrows to both sides. Okay, so what happened to these lines? Did they intersect? Hopefully you're thinking no. That they did not intersect, and now we have to analyze whether or not they ever would intersect. So I'm going to go ahead and say they did not intersect. This is a symbol for that, or no solution. And we're going to go ahead and fill in these blanks. So let's take a look. The slopes are, in this case, the slopes are exactly the same. So I'm going to write that, exactly the same. And the y-intercepts are what? Hopefully you're thinking that they're different. This one is a -3, this one's a +1. So the y-intercepts are different. And I'm going to write they must be different in order for this to work. When graphed, well, the two lines are what? How would you describe these two lines? The blue line and the red line. How would you describe them? If they don't intersect ever, what would we call those types of lines? Hopefully someone's thinking parallel, or hopefully maybe even someone said parallel. Mr. Jordan, if they said parallel, you can give them a red vines from the cabinet just as a little extra treat. So there is how many points where they intersect if they're parallel? There are no points where they intersect. That's why we don't have any red and blue overlap. That's why we don't have any purple. There are 0 points where they intersect, so there is no solution. I'm going to do my best to write this with my mouse here. There is no solution, so there is no number that will make the equations true or equal. Never, ever, ever will we find a number that works for this red equation and this blue equation that are the same. Okay. Let's go ahead and move on to our third one. If you need more time, pause the video. This one we're going to, let's see. Oh, this one is not in slope-intercept form. Okay, so we're going to first convert this to slope-intercept form. And remember, with slope-intercept form, we want to get everything except the y onto, or we want to get the y by itself. So we need to get everything except the y to the other side. And right now, the part that's kind of interfering or invading y's territory is this negative 2x. So we undo this negative 2x by adding 2x to both sides. Bear with me while I have this sloppy writing, sorry. So we're going to add 2x to both sides. And now I have y equals 1 plus 2x, which is really close to slope-intercept form. The only difference is the x comes first. So now I have y equals 2x, and I'm keeping that a positive 2x because this is a positive 2x, and this 1 is also a positive 1. So I'm going to say plus 1 over here. Y equals 2x plus 1. So now instead of looking at this equation, I'm actually just going to kind of cross this out. We're looking at this equation and this equation over here. All right, so let's go ahead and take a look at the slopes here. Are the slopes the same? Hopefully you said yes. The slopes are the same. So we're going to type that in here, the same. The y-intercepts, what about the y-intercepts do you notice here? Hopefully you said they're the same. The y-intercepts are the same. When graphed, there is only blank lines. So let's go ahead and graph these two. So I have my first one I'm going to do in red just to stay consistent. This first equation I'm going to do in red. So we're doing 2x plus 1. So we start on the positive 1, and we're going to go up 2 over 1, up 2 over 1, and it's going to continue on like this. Something like that. And now I need to graph the next equation, which is y equals 2x plus 1. Does that sound familiar to you? Hopefully it does, because this is the line we just graphed. We started at 1, we went up to, oops, that's the wrong tool. We started at 1, and we went up 2, and then we went up 2 more, and we ended up getting this line right here, which it'd be super cool if this turns purple, but I don't think it's turning purple. But this line is now purple in our theory because this line is the same line. We graphed two lines on the same exact spot. So what does that mean for us? When graphed, there is only one line since the equations are the same. So they are the exact same line. We did graph two lines on this graph. It's just you can only see one because they're exactly the same. They're on top of each other. So because anytime lines share a coordinate, they share that solution, we can say that they're sharing infinite coordinates. So therefore, there are infinite solutions. Any number will make the equations true or equal. So we can plug in any value along this line for x and y, and it will make both equations true. All right, so a quick question. Could I have plugged in this coordinate over here to make the equations true? No, because it's not on the line. So I don't like this part. Any number will make the equation true. We should probably write any number on the line will make the equation true. So figure out a way to do that for me on the line. Let's see. You guys know what that means. Something like that. Any number on the line will make the equations true or equal. All right. So once you're finished with this foldable, go ahead and paste it or glue it into your math journals. And then you're going to start working on a Space Invaders practice sheet. And I think you'll have a lot of fun with it. I hope everyone is doing well. I miss all of you. And I'm so excited you're learning systems. Have a great day, everybody.